Assalamu alaikum dear students. Welcome to our YouTube channel CED Engineering Academy. So dear students, in today's video we are discussing MS2 lecture series. In this playlist we will upload the conceptual videos and problem related to mechanics of solid 2 course. So in today's video we will discuss the geometric properties that are very important because in MS2 almost in every problem we are required the geometric properties. So for that reason we will have to calculate the geometric properties. For example, if we have a problem in MS2, these problems in first part we do the force calculation. We find out the forces by equilibrium equations, and in the second part we have to calculate the geometric properties. Geometric properties relates the forces with stresses, relate the forces with its effects that are produced due to it. For example, if we discuss the stresses equation, tau shear stress equation, tau is equal to VQ divided by IB. So in this equation, moment of inertia is the geometric property. Similarly, if we consider the equation of axial stress, which is equal to P divided by A, so here A is the geometric property. The relationship between the force and stresses or deformations is made through the geometric property. So calculation of the geometric properties are required, and we must know how to find these geometric properties and what are those geometric properties. So we have to define the area. Area in simple words, if we define area, we can also define area. For example, if we have a square, it's BH. If we have a triangle, it's half BE into H. But here in mechanics of solid and structure analysis, area is the axial resistance. Okay, it is the measure of axial resistance of a member. The more area, the more it will resist a force. If a cross-sectional area of a member is greater will be the force carrying ability of a member. Area is a mathematical expression, so it's in physical meaning it's the axial resistance. So for regular bodies or for regular shapes we have formulas for areas, but if we have irregular shape body or composite shape body, so how we would calculate the area of this? We have formula for that. A is equal to integral of dA. So for example, if we have this composite area, if we know the equation of this line, when we integrate that we will obtain the whole area. Okay, if we have an equation and we integrate that, we would obtain the area of that section. Or if we have a curve and we integrate that from upper to lower limit, we would obtain the area under the curve. So area is the axial resistance. The second term is the first moment of area. First moment of area is denoted by Q. When we have area, for example here, if we have this area, small differential area, if we find it about this centroidal axis, when we multiply or when we take the first moment of this area, for example y, when we calculate it through z axis and this area, when we multiply with y, we would obtain the first moment of area. It is the first moment of area. Okay, for example, if I draw here some diagrams, this is a square and here it is a triangle. and I say that I am calculating the first moment of area about this reference axis. So for example, if this is the centroidal of the square and here it is the centroid of the triangle, so first moment of area says this is, for example, if this is area 1, this is area 2. First moment of area says a1 y bar 1 plus a2 y bar 2. What is this? This is the distance from the centroidal axis of the area 1 to the reference axis. Okay, this is actually its moment. So when we multiply this with area 1, we would obtain the first moment of area for this section, and similarly if this is area 2 and we multiply it with its moment from the reference axis to the centroid, then this will be, and the first moment of area of this triangular region, and when we add these both of these, we would obtain the first moment of area for whole section about this axis. So this is actually the first moment of area. Its second point is that for symmetrical shape, the first moment of area about the centroidal axis, the first, when we calculate the first moment of area about centroidal axis for the whole section, then it will be 0. How it will be 0? For example, if we calculate the first moment of area for this section, it will have some value that will be in positive, and in the similar manner if we calculate the first moment of area for the lower region, it will also have some value, it will be negative, and when we add these both, it will comes out as 0. So first moment of area for the whole section about the centroidal axis is 0. First, in simple word, first moment of area is the, when we take moment first time with respect to first time, when we multiply area with moment, then this is the first moment of area. Here this area, if we multiply it with y, we would obtain the first moment of area about the z axis, and when we multiply this with z, so we would obtain the first moment of area about the y axis. It can also be write as this one, summation of a y bar and summation of a z bar. So the second term is done. Now the third one is the moment of inertia. Moment of inertia can also be called as the second moment of area, because here we take the second moment, first moment and then second moment of the area. Moment of inertia is a mathematical expression, and it is a measure of the bending resistance of a beam, or in case of column, it is the measure of buckling resistance. The more moment of inertia of member, the more will be its ability to resist the bending moment or the buckling. So if I draw some sections for you guys, it will, I think it will be a good example. If these are two sections, if its height is 4, base is 3, this is 2, this is 6. So if for example this area will also be 12 and this area will also be 12, so it means that its axial resistance is same because its area is same, but its moment of inertia will be different. Okay, because here the cube component bh cube by 12, the cube component is 4, here the cube component is 6. Moment of inertia of this section will be greater. In other words, its bending resistance will be more here in this case. So here you can see how the geometry determines the strength, as well as its buckling resistance will also be greater. In both cases the area is same but its resistance are different. So that's why the geometric properties are important. You have to understand these things. If we calculate the moment of inertia about z-axis, this one is the z-axis. If we calculate the moment of inertia of this region, so we have to multiply with this area with y square and integrate it. Similarly, if we calculate the moment of inertia about y-axis, we have to multiply with area with z square, which is this distance moment arm, and then we have to integrate it. We can also find the moment of inertia by parallax theorem. So actually this parallax theorem, the moment of inertia by this parallax theorem are for composite bodies or for unsymmetric regions where the shape is not symmetry about its axis. For example, in this case we can use this formula, or in L shape, in T shape, we can use this formula. So this was the example of moment of inertia. The fourth part, we have the polar moment of inertia. Actually the moment of inertia, we consider the second moment of area about the x-axis or z-axis. It means that moment of inertia can be found only with respect to z-axis or y-axis. But in case of polar moment of inertia, if I consider this 3D diagram, the polar moment of inertia can only be found on axis that is perpendicular to this cross section. For example, in this case, the axis that is perpendicular to this cross section is x-axis. So that moment of inertia which can be found with respect to x-axis, it is called polar moment of inertia. And where this polar moment of inertia is used, this polar moment of inertia is used to calculate the torsional stresses in a circular shaft or a beam. Where this moment of inertia is used, moment of inertia is used to calculate the bending stresses, flexural stresses, which is equal to mi multiply y. And where this q is used, first moment of area is used to calculate the shear stresses, which is equal to vq divided by ib. And where this area is used to calculate the axial stresses. So all these geometric properties are used to calculate the stresses. So now come towards the polar moment of inertia. It can be only found about the axis which is perpendicular to the cross section. So this cross section, the axis that is perpendicular is x-axis. So for example, this diagram, this is in 3D. I have drawn here in 2-dimensional. So if we calculate the second moment of area about the y-axis or z-axis, that will be called as moment of inertia. But if we calculate the second moment of area about this line, which is rho, if we calculate the second moment of area about this rho, so actually this will be called polar moment of inertia on x-axis. Okay, so this rho, from the Pythagoras theorem, this rho will be equal to y square plus z square. Here is the mathematical expression of the polar moment of inertia, integral rho square dA. So here rho will be equal to z square plus y square. If when we integrate it, it equals to the rectangular moment of inertia, which is in this case, if you multiply dA with this z square and y square, it will becomes iy and iz. So in simple words, we can also say that polar moment of inertia is equal to moment of inertia about y-axis plus moment of inertia about z-axis. So this was the polar moment of inertia. Now we have to discuss the product of inertia. So what is the product of inertia? Product of inertia not means that it is the product of the two moment of inertia or product of the two things. It is actually the moment of inertia with respect to two axes. For example, here I, y, z, we will calculate the moment of inertia. We have to calculate its inertia about the two axes. For example, here both with respect to y and z axis. So that will be called as product of inertia. It can also be written as summation of a y bar and z bar. Now what is the y bar and z bar? We will also discuss in the upcoming problem. This y and z is the centroid to centroid distance. Okay, the centroid distance, for example, the centroid of the one section to the centroid of the whole body, the distance from the centroid of the section to the centroid of the whole body with on y axis and z axis, those distances are y bar and z bar, and this formula is for composite section. For those sections which are not symmetrical, we can also find product of inertia by this formula. And the second point is that product of inertia about the principal axis are zero. Actually, how we can define the principal axis? Principal axis are those axes in which these are actually the two orthogonal axes. In first axis, the moment of inertia is maximum, and in the other, the moment of inertia is minimum. And the second point in principal axis is that product of inertia on principal axis is zero. Now, how we would verify this and how we can say that product of inertia about the principal axis is zero? I will show to you guys. So, for example, this is the again the rectangular cross section. If this is its principal axis or centroidal axis, z and y, this is z plus z, this is plus y. Okay, so if this is area 1, this is area 2, this is area 3, this is area 4. So we have a formula for the product of inertia. For example, I y z is equal to summation of I y z plus a y into z. So this is for one section. We know that product of inertia, these terms for the symmetric object will be zero because the product of inertia of the individual section here will be zero. In this case, its principal axis will be this, and on principal axis this product of inertia is zero, and we are left with a, y and z. So for this whole part, if we find product of inertia total for the total bar, how we would say the product of inertia of area 1, its distance is y and z, plus area 2, its distance is y and z. Similarly, area 3, y and z. Similarly, area 4, y and z. So here the thing is that in this first quadrant, the y is positive but the z is negative. So here z will have negative value. We can also say that it is symmetrical body, and here all parts have the same area, and say this distance is y and z. So here the y is positive, z is negative. This whole calculation will have negative value. Similarly, for this second part, both are positive and the area is also same. So this product of inertia of this second area will have positive value. So this positive and negative will cancel each other. Both magnitude will be same. It will becomes zero. In this case, similarly in the third, both are negative. The y is also negative, z is also negative. So in the third area, z axis is also negative. These axes are not just like the x and y axis, in which this was first, this was second, this was third, this was fourth. X, y and z, y axis are different. Okay, here we have first quadrant, this is second quadrant, this is third, this is fourth. Okay, so its sign conventions are also different. Here it's positive and here it's negative. So in the third area, both values are negative. So negative, negative, this will positive value. This value will be positive, whole product of inertia. And in the fourth part, here the z is positive but the y is negative, y axis. Here its value will be negative. So positive, negative, its magnitude will be same because our area are same and the distances are also same. So here it will 0. So in this way the product of inertia about the principal axis will be 0. Similarly, in the other case, when we move toward the centroidal axis, that what is meant by centroidal axis? So centroidal axis is a geometric center of the body. Okay, centroidal axis, if the object is symmetry and its axes are also symmetrical, its centroidal axis are known. Okay, so how you would find the centroidal axis? We have a formula summation of a y divided by summation of area. So we can also say that, for example, if we have some areas, for example, in the similar case, if I have these two areas, this is centroid and this is the centroid of the triangle, this is centroid of the square. If I calculate its centroids of the whole section, how I would calculate its formula? For example, its formula is for y, it is a1 y1 divided by a1 y1 plus a2 y2 divided by a1 plus a2. So here this is a1, this area of the square, area of the triangle is a2, and what is y1? Y1 is the reference, is the distance from the reference axis to the centroid of the square, and here the y2 is the distance from the reference to the centroid of the triangle. When we know these values, y1 and y2, multiply it with area, add it, and then divide it by summation of areas, we would locate the centroid distance from the reference axis about y axis. Similarly, in case of z, its formula is also same. Its formula is a2 a1 z1 plus a2 z2 divided by a1 plus a2. So we will calculate its centroidal distance from the reference axis z axis, z distance or location. So this is the formula for the centroidal axis. In case of y, if we locate the y centroidal axis, its formula is summation of a y divided by summation of area, and in z axis its formula is summation of a z divided by summation of area. So these are the some concepts of the geometric properties. Hope you learned. Inshallah, in the next video we will solve problem. So if you learn from this video and it's helpful for you, do subscribe the channel, also like the video. Inshallah, we will meet next time. Thanks for watching.